Hey everyone. We're gonna get started so that we stay on time. So welcome to this week's biome seminar. This week we are super pleased to have Dr. Danny Ibarra. Over the last 15 years, the Yale School of the Environment has held this weekly seminar series, which we have named Biomes, which has been the school's flagship forum for bringing cutting-edge research and impactful work to the community. Biome stands for Bridging Issues and Optimizing Methods in the Environmental Studies. As such, I'm really excited to be able to introduce Dr. Ibarra, the Manning Assistant Professor of Earth, Environmental, and Planetary Sciences and Environment and Society, and an affiliated Assistant Professor of Engineering, all at Brown University. Dr. Ibarra is a biogeochemist and climate scientist. His research is centered around studying modern rivers and catchments, as well as the terrestrial geologic record, meaning lakes, soils, and caves, to understand Earth system level processes that link the biosphere, atmosphere, and lithosphere. His research aims to gain a better understanding of how anthropogenic climate change impacts radiative forcings, including ongoing field trials. Dr. Ibarra uses geochemical measurements, field observations, reactive transport modeling, hydrologic modeling, and other syntheses of climate model outputs to answer these questions. So with all of that, please help me welcome Dr. Ibarra to the stage.
Awesome. All right. Well, thank you, Robbie, for inviting me, and I'm really pleased to be here. So today I'm going to mostly talk about modern weathering processes, not so much in enhanced weathering type fields, but looking at sort of modern catchments in a variety of places. That work is really motivated by wanting to understand the long-term carbon cycle and the links between the short-term and the long-term carbon cycle. And specifically today, I'm going to focus on lithology and the mineralogy related to these weathering reactions, as well as in the second half of the talk, really focus on the cryosphere. And this work is really the product of work by my former postdoc, Evan Ramos, who's now a new professor at University of Pittsburgh, and one of my most senior graduate students, Sebastian Munoz, who y'all should look at for a postdoc in the future, in a year or two. So really all the credit goes to them, and you'll see their names on the slide quite a bit. So I think a lot of us who study river systems or soils and catchments, we grab water samples, right? And we think about that water sample, and we measure the various cations and anions in that water sample, and we want to ask the question, what controls the efficiency of those solutes that we measured? What is the reason that this water sample has calcium concentration of X and bicarbonate concentration of Y? And so today I'm going to really focus in on two things that likely control the efficiency of solute and alkalinity generation. That is lithology, what you're weathering must matter. And this is, of course, being leveraged by those here at Yale and elsewhere working on things like enhanced weathering. And what is the role of the cryosphere, right? The cryosphere in this example of the Gulf of Alaska, where I'll show you some of our recent work, is grinding up rock. It's a dynamic process. It's changing the geomorphic landscape parameters related to the river systems from those catchments. Okay, so thinking about the long-term carbon cycle, some of you may not have sort of thought about the long-term carbon cycle, but the long-term carbon cycle over 500,000 year to 10 million year timescales is in relatively close balance. And we know this from the geologic record and by the virtue of the fact that we're here on Earth, it's remained habitable for a long time. And so that means that the inputs to the exogenic carbon cycle, to what controls the atmospheric CO2, have to relatively closely balance the outputs. And today I'm going to talk about both the left side of this diagram in terms of silicate weathering, but I'm also going to talk about organic carbon burial and also get into an interesting proxy that has emerged out of folks in the UK related to organic matter oxidation from petrogenic organic carbon. So just the agenda for today, I'll sort of introduce, for those that haven't seen it, the canonical view of the global carbon cycle and sort of what I learned when I was an undergraduate, some of which was developed here at Yale, and then talk about these less well-studied fluxes. And then I'll dive into some modern weathering studies linking weathering and organic carbon and really focus on lithium isotopes and uranium isotopes that allow us to trace these things. And then, as I mentioned, I'll focus on this interesting new emerging proxy to understand the oxidation of petrogenic organic carbon in catchments that are dominated by sedimentary or metasedimentary catchments. And then I'll sort of zoom out and think about in a broader lens, sort of the role of ice sheets versus glaciers as a source versus sink of CO2, and perhaps sort of provide some nuance on what has recently come out in the literature. So this is the canonical view of silicate weathering, as sort of described and solidified over the last 50 or 60 years, starting with Walker and Berner here at Yale, thinking about this balance between volcanic degassing and silicate weathering, and then the ultimate burial of that carbon as calcium carbonate. And so, these fluxes are important. We've measured them in rivers. We understand that these fluxes and their relationship to how warm or cold the Earth is, how hot or how warm or cold or how wet or dry the land surface is, may impact what these fluxes are, which establishes what's known as a negative feedback between atmospheric CO2 and these silicate weathering fluxes. And this is sort of a canonical thing that's taught in many textbooks about the carbon cycle. So what do we mean by negative feedback? This is one way of representing it, is on a diagram like this, you have steady state CO2 on the x-axis and your input and output fluxes on the y-axis. And the negative feedback is essentially the slope related to the relationship between steady state CO2 and these fluxes. And one pretty intuitive way of illustrating this is thinking about what happened when we evolved plants, right? And this is something I've worked on, and I'm not going to talk about in detail today, but when you evolve plants, you likely strengthen this feedback. So that is to say that you make this feedback slope stronger temporarily on the sort of evolutionary timescales of evolving certain plants like gymnosperms during the Paleozoic. You increase the output flux, so you increase weathering rates, and thereby, in the long run, decrease atmospheric CO2. And so this has been invoked by many to be the sort of the net effect of what happens when you evolve plants. But such strengthenings of such feedbacks could happen due to changes in the location of continents, the lithologies that are available. For one interesting example is like that as part of us adding basalt to agricultural fields, we're trying to strengthen the feedback to some extent of the Earth system, and basically do this upward flux to mitigate against atmospheric emissions. I will not be talking about the geologic record much today, but I just wanted to mention that we have tools available to us, and we can run long-term carbon cycle models to understand how this feedback strength has changed over the long term. And so this is some modeling that I did with Jeremy Caves-Rugenstein back in 2019 in a paper where we modeled the Miocene relative to today. And here is the same plot here on the left, but actually, sort of model results related to this feedback strength change, this change in the silicate weathering flux. And what we basically do is we invert the lithium isotope record as well as other constraints that we have for the carbon cycle. And we say that the feedback strength has changed since about 15 million years ago. What does that mean for those of you interested in the geologic record? This means that the Earth system is going to be able to faster draw down atmospheric CO2 on the sorts of tens to 100,000 year timescales. And so shown here on the right, I've taken the model and I've just injected it with a forcing of atmospheric CO2 or CO2 to the atmosphere, and I'm allowing that forcing to decay and be drawn down. In the solid line is today, in the dashed line is the Miocene, using the constraints that we derive from this model. So this is why people have sort of thought a lot about these feedback strength changes in terms of silicate weathering for many decades now. And unfortunately, or in some ways fortunately, there's a lot of disagreement between what we put into these long-term carbon cycle models. And so here's the same sort of plot, PCO2 versus some weathering flux. as it looks in geocarb, Gini, COPS, LOSCAR. So for those of you that know these models, these are models that are run on 10 million or 5 million year timescales. And you can see that the slope of these curves is dramatically different among these models. And so, we'd like to have better constraints on this because ultimately the slope of these curves defines the negative feedback in the model. So what might control these feedback strength changes, right? These are things that we think about that may influence the slope of this reaction at a global scale or at a local scale. And so that could be the thermodynamics and kinetics of the reaction, which are related to the lithology and the weathering products, such as the clays that are forming in those weathering reactions, the water cycle, right? And linked to the water cycle is, of course, land plants and probably the coupling of land plants to organic carbon burial. And then, as I've already said, continental configuration. So, this is all well and good for silicate weathering. And then lastly, I just wanted to acknowledge, one thing that we really know is that lithology plays a really large role. And so here's a plot from one of my chapters of my PhD work for silica on the top and bicarbonate on the bottom. And these are modern USGS and elsewhere catchments where we've defined the concentration discharge relationship between bicarbonate or silica versus runoff. You can think of this as climate as well. And you can see that the basalts in general, have higher fluxes and also higher overall concentrations than the granitic catchments. And this is well known, and this is exactly what we're leveraging in sort of enhanced weathering type work. Okay, so that's all well and good, right? But that is just this flux here and its relationship with climate and with the feedbacks that we might be trying to alter or that have been changing through the past. There's kind of an emerging view, and this is taken from Hilton and West in one of their large review papers of the long-term carbon cycle, in which we have sort of subequal fluxes to the silicate weathering that have been overlooked or previously assumed to basically balance one another, that are likely very important for the long-term carbon cycle and probably also for the short-term carbon cycle, and really link the long-term and short-term carbon cycles. And so those fluxes that I'm going to talk about more today than just the silicate weathering fluxes are the erosion of biospheric organic carbon. So that's a sink. The oxidation of rock organic carbon. So that's a source of CO2 to the atmosphere. And then sulfide oxidation. This is the oxidation of minerals like pyrite and the subsequent carbonate weathering that occurs with that sulfide oxidation. Unfortunately, we're still sort of at the point where we don't have the large data sets necessarily for these things to better parameterize all of these feedbacks. They're in a lot of the long-term carbon cycle models, but I would say they're even less well understood than the traditional sort of silicate weathering. Okay, so what controls the efficiency of solute and alkalinity generation, and what's the role for lithology? And I'm going to sort of first start with this lithology question, and then we'll move on to the cryosphere. Actually, some work by a newer professor here at Yale inspired some work that I did with Evan Ramos as part of his postdoc with me and Mark Torres, is sort of asking the questions, can we observe links between weathering, and that is the clay formation that occurs during weathering, and organic carbon? And that is to say, is there links between the silicate weathering and organic carbon burial on short time scales or as we see in the modern? So essentially asking if this arrow here on the left, the dark blue arrow, if this is somehow linked to this black arrow on the right of this mass balance diagram. And they're obviously in different pools, and so we have different tracers for silicate weathering versus organic carbon. But there's one tool that I think is particularly useful, and that is the lithium isotopes of clays or suspended sediments in rivers that allow us to potentially track this linkage. And I'll sort of show you what I mean by that. So lithium isotopes reliably trace silicate weathering and clay formation in that there's mostly all the lithium is in silicates. Secondary clays preferentially incorporate lithium-6 over lithium-7, meaning that the clays will be depleted relative to the rock. And there's no real observable fractionation by plants or algae. So it's very useful in that if you're just dissolving some rock, you're going to look like the rock. And if you're going to dissolve some rock but precipitate clay minerals or secondary minerals of some sort, you're likely to then the fluid would then be enriched in delta-7 lithium, and the clays would be depleted in delta-7 lithium. And so this is a useful tracer of silicate weathering in the modern catchments and soils that we can look at. So what we did is we compiled some data from the Hawaii chronosequence data sets from these two papers shown here that have both lithium isotopes in the soils as well as organic carbon contents in those soils. And this is a site that is well known for looking at the transformation of partially crystalline minerals to clay minerals over this chronosequence that goes from just a few thousand years old to millions of years old. And we also looked at suspended sediments in two settings, one from the Little Deschutes River in Oregon and from the Rio Bermejo in South America. And I'm not going to get into like all the details of these study sites, but what we did is we measured the delta-7 lithium and the percent organic carbon, or we compiled it from the literature. So I'm just going to show you the data. So on the top here, on the right, is organic carbon on the y-axis versus the difference between the delta-7 lithium and the fine fraction minus the rock. And you can see that it's less than 0. And it's variable across these sites, but we seem to have these negative relationships. For the Rio Bermejo, there's relatively little organic carbon, and so you have to really zoom in on the axis here, down less than 0.5%, and you do see this relationship. The Little Deschutes are very low in delta-7 lithium in the fine fraction relative to the rock. Suggesting that you have a lot of this clay formation occurring, and potentially it looks like protecting organic carbon. And so if we infer from the y-axis here, or the x-axis, that to the left is increased clay formation overall in the weathering zone in the case of Hawaii, or the overall catchment in the case of the Little Deschutes or the Rio Bermejo, and then the y-axis is, of course, the percent organic carbon. We are basically seeing this linkage and this relationship between the two, right? But it's not one universal relationship. It appears to be different among the different catchments or different study sites. One clear difference is the type of bedrock, the climate, and the crystallinity of the clay materials. One nice example of that is that in the Little Deschutes, this was a catchment that was glaciated during the last glacial maximum. So it's very young weathering profiles. And so we basically have incipient weathering occurring, and we have halloysite forming. Versus in Hawaii and a lot of the older soils, we have a much more crystalline kaolinite. So same stoichiometries, but there's clearly a difference between the amount of lithium isotope fractionation occurring between the kaolinite-dominated Hawaii and the halloysite in the Little Deschutes, despite, as you can see, very similar overall organic carbon contents of those soils or those suspended sediments. Okay, so with that, we sort of came up with this conceptual model that's really built off of a lot of previous work related to this field, where we're thinking about the breakdown of bedrock and the formation of clays through the dissolution of that bedrock and the occlusion of the slow organic carbon, the hard to oxidize organic carbon in the weathering regolith sort of profiles, and thinking about this sort of linkage here on the left side of this diagram. And so I've been thinking about, what are other isotope proxies that perhaps tell us something about this lower process that can be paired with the sort of occlusion of organic carbon with clays that's shown here in the blue arrow. And so I kind of went back to my roots and went to an isotope system that I actually worked on as an undergraduate with Claire, sitting here in the front row when we were in the same labs together, uranium isotopes. And so uranium isotopes are interesting in that on the surface of grains, when uranium-238 decays, you damage the mineral lattice. And by damaging that mineral lattice, you have what's known as alpha recoil. And so most waters on Earth, most river waters, if you just pick up an average river or groundwater, are going to be enriched in uranium-234 relative to the overall equilibrium in this decay chain, which some of you who know this will go all the way down to lead. But we're just considering the uranium-234 relative to 238, and it's out of equilibrium in river waters. And so what we wanted to do is ask the question, is there some linkage between the lithology and this uranium-234, 238, as well as then pairing it to the lithium isotopes that are tracking this clay formation process. And so the hypothesis, therefore, was that sites that are fine-grained and have a lot of surface area, sedimentary rocks, when they're weathering, would have an increased 234, 238, and sites that are highly crystalline, not as erodible, such as metamorphic rocks or more crystalline volcanic rocks, are going to show less enrichment in 234, 238, and that we should then therefore see these sorts of arrays in this space here between the lithium isotopes recording the clay formation and the uranium 234, 238 values. And so I'm now switching from the clay fraction in the last part to now I'm going to show you data from the dissolved side. So this is what, when you go pick up that water from the river, what you actually see. So we're currently generating the first data sets from my lab of this sort of work. But what we did initially is we looked at the literature, and people have paired these two systems before, particularly in Iceland. There's been a lot of nice work done on these paired lithium isotope and uranium data sets. And we classified all the catchments based on their bedrock and paired the samples when they hadn't been paired. You can see there's a nice sort of control for climate in the data set that does exist from New Zealand. And so what do you see? Well, we see what I sort of showed you in that schematic, in that the paired lithium isotope and uranium isotope data suggests this role for rock type underlying a catchment and the comminution of that rock type in setting clay formation and setting the relationship between these two isotope systems. And so this was exciting when we sort of pulled this up, and unfortunately, we don't have a lot of data sets of this nature, but I can tell you, you can also look at, for example, lithium over sodium versus just uranium concentrations, and you can see similar sorts of trends across much larger global types of data sets. I won't get into the details today, but then the natural thing as a geochemist is then you build a reactive transport model, and that's what these lines here show, is that you can vary parameters such as grain size, uplift rate, fluid flow rate, kinetic rate constants, and try to model this array that you see here. And really the changes in grain size are an important control on setting the arrays that we see in the observations, at least as modeled by our reactive transport model. Okay, so that's kind of the role of lithology. And now I'm going to think about the role of lithology still, but also what does the cryosphere do to all of these underlying weathering fluxes that we see. And I'm going to really focus on the Gulf of Alaska that's shown here. In a couple cases, looking at a site in South Central Alaska where we have a sort of space for time substitution going on with a suite of catchments with variable glacial cover. And then also look at all the USGS gauge network that is available from the Gulf of Alaska, which is quite substantial. And so now we're going to focus on quantifying sulfide oxidation and the subsequent carbonate weathering, which is a source, and I'll show you the equation for that in a second, of CO2 to the atmosphere, as well as the organic carbon oxidation from these catchments. You can imagine that this sort of tectonically active area has a lot of meta sediments that have been abducted, so ancient ocean sediments that have been abducted, and so therefore they're a potential source of petrogenic organic carbon that can become CO2 in their oxidation during the weathering process. Okay, so for those of you in this sort of general field, you'll likely know this paper from Mark Torres, my collaborator in PNAS, in 2017, where he looked at all of the river chemistry data that's all plotted on here from the world, and he focused on the glacial catchments. That is to say, catchments that are impacted by some, I can't remember what the threshold is, but a relatively large glacier or ice sheet sitting over those catchments. Here's the data, sulfate over sodium versus calcium over sodium. And the key observation in the blue is that there's a subset of these glacial catchments that are relatively enriched in both calcium and sulfate, right? And this represents the reaction that's shown here on the right that's considered a potential source of CO2. So pyrite is not a substantial by weight mineral in metasediments. However, it's of sufficient amount that when it's oxidized by either of these two reactions that's shown up here, you produce some amount of sulfuric acid. And this sulfuric acid can weather carbonate or silicate minerals, but unfortunately, when it weathers carbonate minerals, it then becomes a source of CO2 to the atmosphere over long time scales, right? And so how much pyrite oxidation is occurring and the concurrent carbonate dissolution using the sulfuric acid that's generated from the pyrite is therefore a potentially important player that the weathering community has really started to think about a lot more. And so the hypothesis from this review paper from Hilton and West is that that you would have in these cooler climates where you have glaciers or ice sheets sitting on metasedimentary rocks that could potentially become sources of CO2 to the atmosphere ocean system. So this work has motivated us to try to really focus on the work in the Gulf, this work in the Gulf of Laxa that we've published in 3 or 4 papers now over the last couple of years, because it's an interesting place to do this, and it has a lot of variable ice cover, as you can see from the white that's shown here on this, the white that's shown here on this map. And so here's again just the sort of the hydroclimate and the geography of the Gulf of Alaska. Looking at the climatology here on the bottom here, here's precipitation, and here's the sort of air temperature. You can imagine that the glacial melting, which is going to play an important role here, is somewhat scaled or related to the air temperature changes that occur. But then you also have increased precipitation in a lot of these regions in the sort of the fall time period. So we have been working on some local sites, but then we've also been looking at the USGS data sets. And so here is just what all that USGS data does look like. Shown here on the left is the total dissolved solid versus the total suspended sediment yield. It's a very strong relationship because this is a highly erosive place in the world, so they're highly correlated. That's for all of the data that exists. This is when you average across the catchments, and we're coloring things by their glacial cover. And so we did look at what's known as the concentration discharge relationships and the fluxes from the USGS data set. Shown here is the results of looking at these concentration discharge relationships. And so the y-axis on the top 2 plots here is what we call the power law slope. And this is basically distinguishing between so-called chemostatic or flat concentration, so no change in concentration with a value of 0, and a pure dilution would be -1. And we see some interesting but not super significant correlations with slope on the left top here and glacial coverage on the right here. It should probably be of no surprise, though, that you have with increasing glacial coverage versus just the yield. So this is the area normalized weathering flux, essentially, for silica, calcium, and bicarbonate. But particularly for bicarbonate and calcium, we see these positive relationships as a function of the amount of glacier. Glaciers are grinding up rock, they're increasing surface area, they're allowing a lot more of these weathering reactions to occur uninhibited by surface area constraints. And then shown here is we also see this positive relationship in the overall cation yield in this region versus glacial coverage, something that wasn't seen in the Torres et al. Global compilation. Okay, so now we're going to zoom in on this series of 5 catchments in South Central Alaska that drain into Ketchimek Bay. For those who have been to this part of the world, this is Homer, Alaska. It's a really gorgeous place. We take a boat from Homer across to each of these outlets and get to do some really fantastic and special field work in this site. And the University of Alaska Anchorage has been monitoring these catchments for almost 6 years now, and we have continuous data sets to look at, and they're continuing to look at this. And just for reference, I titled this slide "A Rapidly Deglaciating Landscape." Less than a century ago, where we sample in the GRU ink is where the glacier toe was at the in the 1950s. So this is truly a rapidly deglaciating site. So you're uncovering a whole bunch of this really ground up metasedimentary rock and being able to progress these weathering reactions. Okay, so I will show you a bunch of these results using what's called an RZ plot. It's basically a model inversion for getting at the silicate weathering versus carbonate weathering fraction on the x-axis versus the amount of acid that comes from the sulfuric acid weathering reaction that I showed you earlier for the pyrite oxidation. And this is just a paper that describes these RZ plots from Mark Torres and Preston Kenemy from a few years ago in AJS. And they've basically shown here what a bunch of rivers from the Andes looks like. How do you do this type of inversion? Well, what you do is you put in your river chemistry, you define end members. And so this is the actual data from Ketchimek Bay from the South Central Alaska sites, colored by glacial, the proportion of glaciers, where the green is less glacial coverage and the blue is more glacial coverage. And you define these various priors in the model. And you have, you can add other things like sulfur isotopes or strontium isotopes, and it allows you to invert for essentially the X and the Y axis here and put individual samples or catchments in this space. The important part is that if you're in the bottom part of this diagram, you're silicate weathering dominated and you're a long-term sink to the atmosphere. If you're in the upper part, you're a long-term source to the atmosphere. And in fact, if you're in the top right, this dark region, you're a short-term source to the atmosphere. And this is just related to the differential resonance times of sulfur versus carbon in the atmosphere-ocean system. Okay, so here's what the data look like for this suite of sort of space for time sites that we have from Ketchimek Bay, where the green are the sites that have very little glacial coverage, and the dark blue are the sites that have the most glacial coverage. And you can basically see that going from the northeast to the southwest on this map, we're moving from this long-term CO2 source region into this long-term CO2 sink region, suggesting, right, that as things deglaciate, we're using up, perhaps is the way to think about it, the available pyrite to get oxidized. And so then as you transition to these sites that have no or little glaciers, you're moving into a site that's just dominated by more typical silicate weathering and carbonate weathering. So that's what we observe across this set of sites, controlling to some extent for bedrock and climate. And I will just mention that we can do this in a variety of different ways to then calculate the CO2 balance for these catchments. And so here I'm showing the average estimate on the left here using the average data from each site. You can account for CQ changes, which makes things a little bit messier. And you can add in things like strontium isotopes. But the general view also is that as you move down in these sites, you're also reducing the overall yield because you no longer have the glacial melting that's occurring, right? We made these catchments are out of hydrologic balance. They're losing a lot more water in total than they're gaining in any given year because of the warming that's occurring in South Central Alaska. Okay, so does this work across the Gulf of Alaska, right? So I asked the PhD student at University of Alaska Anchorage to do the same calculations, but do this for all of the USGS sites that are available draining into the Gulf of Alaska here. Of course, we've now got some complications related to the fact that some of these sites have minimal metasedimentary rocks in them, but in general, we find the same sorts of trends. So in the blue here is the glacial sites, and the green are these no glacial sites. And you can really see, right, that there's a similar plotting of these data points where each point here is one of the USGS gauges as we saw in Ketchumek Bay. And we just show the histograms on the X and Y axis here. And then we also, classified this as percentage of glacial cover. And you can see that the high glacial cover, which are the squares, as well as the medium, the diamonds, sort of mostly sit in this long-term source of CO2 to the atmosphere, whereas most of the other catchments sit in this sink, silicate weathering dominated zone. So that's what we found for this sort of part of the story. Okay, so that's interesting. But there's another flux that a lot of people have been starting to worry about a lot more, and that is when you uncover these sorts of rocks and you make them available to oxygen, you might oxidize a bunch of the petrogenic carbon that's available to you from these sedimentary rocks. And you can see from the fluxes that were compiled here by Hilton and West is that it's possible that the petrogenic flux is even larger than the sulfide oxidation flux and possibly subequal to the silicate weathering sink, right? And that's a problem if you want to balance all of these various fluxes that we know have to be tightly balanced on over geologic time at least. So we're turning to a proxy for organic carbon oxidation in a metal, rhenium, that is extremely unabundant, but is enriched. It is enriched in for reasons related to redox chemistry in ocean sediments that are high in organic carbon. And it is variable in those ocean sediments, but we can quantify that. And so, what sort of inspired this? This is a really nice study that came from 2017 by Horan et al., where they took a series of sites that had, again, differences in the overall glacial coverage. And they found that the glacial area normalized for the overall watershed area versus the rhenium concentrations scaled rather nicely, right? And this group led by Bob Hilton at Oxford has now shown this across a series of other sites, and that it appears that the rhenium proxy is a nice tracer of the amount of organic carbon oxidation that's occurring as these weathering reactions that we're talking about are also simultaneously occurring. And so we wanted to test this across our sites. And so I had my student Sebastian analyze rhenium across the series of 5 sites that we've been looking at. And so I'm showing you here the 3 lower percent cover sites, Halibut, Tutka, and Jakalov. You can see there's sort of a trend. But it was very interesting when we plotted the 2 sites with the most percent cover. We ended up seeing some of the lowest concentrations in the site that has the greatest glacial cover. And so this is opposed to what's been observed in some of the other settings. And so then the question, of course, becomes, what is going on? Well, one thing we know is that we have proglacial lakes that are developing as these glaciers and ice sheets are this ice sheet and glacier are melting, right? And you have sort of floodplains that are adjusting to all the geomorphic change occurring because of the retreating glaciers. And so I'll just quickly look at the seasonal dynamics because I think it's interesting and no one has done this, but I do think it's related to probably redox dynamics associated with longer residence times in these subglacial lakes. So here's all the data in terms of month versus rhenium concentration. A little hard to see. But in the Gruing site where we have this proglacial lake that's rather large and has developed, you essentially have steady concentrations through time, right? And so, suggesting that there's little sort of dynamic occurring on the seasonal cycle in terms of the amount of petrogenic organic carbon that's being oxidized. In the Wazinski, which is one of the sites that's perhaps lower than we would have expected in terms of its rhenium concentrations, we do see an interesting dilution effect as you go into the wet season, when you see the peak precipitation and you're sort of at the tail end and also peak glacial melt, sort of tail end of glacial melt, you see the lowest concentrations in the rhenium. And we see this also in Halibut, which is one of the intermediate catchments that's shown here. And so And then finally in Jackalob, the site that's depleted essentially of a lot of its organic carbon in the weathering zone. At least that's how we would interpret this. It has essentially a flat profile as well versus month. So it's hemostatic to some extent with respect to rhenium. I think this is evidence, and we're still sort of pondering this data, and we have some measurements of the rocks to do, that the impact of these proglacial lakes, as well as the adjusting landscape, is showing a different observation than one was observed in New Zealand. And so this proxy is promising, but I think it has some nuances that we haven't really thought about as a community yet. And so we'll be eager to see what other people think about that. Okay, so just to wrap up, I wanted to show some modeling associated with what this means for sort of the last few million years and the long-term carbon cycle. And I like to point out to people when I talk about paleoclimate work is we've spent much of the last few million years in glacial periods with large ice sheets, like the Laurentide ice sheet over Canada or the Scandinavian ice sheet over Northern Europe, than the deglacial that we live in today, right? So there's a lot more blue than there is red over the last 800,000 years here, for example. And so these ice sheets, likely matter quite a bit. And this is sort of what was proposed by Torres et al. In 2017, saying, perhaps you have some additional source of CO2 to the atmosphere when you have these large ice sheets because of those weathering reactions related to pyrite oxidation and carbonate dissolution. And so we wanted to recompile this data set as well as look at the data that exists from the ice sheet. So from Antarctica and from Greenland themselves, which wasn't previously included, and do the same RZ partitioning modeling to look at the source versus sink of the catchments and the waters as implied by the waters in this data. So here's the data that exists for ice sheets versus the sort of glaciarized catchment data. On the left of this box and whisker plot is the global alpine data set. Then you have Greenland and Antarctica. Antarctica has very high total dissolved solid because of very long fluid residence times associated with the subglacial waters. Greenland is much more wet-based and it has similar concentrations to most alpine glacier sites. Granted, there's not a lot of Antarctica data. I'll give that as a caveat. So you can put this through the sort of same set of calculations that I showed you for the Gulf of Alaska, and you can see the blue are somewhat scattered, but are mostly in this long-term source area, sort of validating what Torres found back in 2017. And you can see that the green and the red are in this long-term sink, right? And so this is in opposition to this idea that by having ice sheets, you potentially increase the overall source of CO2 to the atmosphere. And so we also do have to estimate discharge to then try to calculate these this sort of the fluxes to the atmosphere-ocean system from the various ice sheets and mountain glaciers that would have existed. And so we do this for the last glacial maximum, and we use climate model simulations of basically P minus E over the ice sheets and the mountain glaciers to do so. And so we can then calculate whether, sorry, this is a little blurry, the CO2 source or sink per year from these various alpine glaciers, Greenland and Antarctica, assuming steady state LGM scenarios, ice gain, right? Because over time you have to build those ice sheets, or the much more rapid ice loss. When you deglaciate from the last glacial maximum, you have a relatively fast, over 10,000 year ice loss. And so putting these distributions of the CO2 balance through the set of calculations, you can see that the global alpine is always going to be a source on average to the atmosphere of CO2. Greenland is going to be a slight sink, and Antarctica is a large sink relative to Greenland. Although we sort of have to remember that neither of these do represent what, say, the Laurentide ice sheet or the Scandinavian ice sheet might have necessarily looked like. And so we can sort of do this modeling and think about what proportion of discharge from the cryosphere came from ice sheets to the right on this diagram versus from glaciers on the left here. And previously, Torres et al. In 2017 suggested 22 ppm per 10,000 years. So that's suggesting that the last glacial maximum was 22 parts per million higher in atmospheric CO2 than we would have thought, than observed from the ice core record. But what we actually find is that it's sort of a wash, basically, because you have some mixing between the ice sheet sink and the glacial source. Likely the cryosphere has no impact on the overall mass CO2 budget via the weathering reactions that we're talking about. And so, this is this sort of negative feedback via this oxidative weathering that was invoked in this work, and sort of we're basically revising this. I will mention that this is all very dependent on how much subglacial melt is actually, so basically how much of the water that's on ice sheets as part of ice sheets actually interacts with rock. So that is to say how much of it is just discharged as icebergs and ice, as opposed to melts and is liquid water, and therefore has some chance to interact with the underlying rock, right? So to wrap up, I hope I kind of showed you these emerging views for how the long-term carbon cycle is balanced and how it interacts with the short-term carbon cycle and organic carbon. It requires this development of newer isotope tracers, like I showed you, and I think there's lots of great work here being done on these sorts of things. The role of the cryosphere and ice probably drives sulfide oxidation and carbonate weathering is clear. And we probably expect to see shifts due to the deglaciation and warming and the changes in the hydrology, right? As we change the snow versus rain, for example, in the Arctic or the subarctic in terms of what we see. Our preliminary results on this deglaciating landscape kind of complicate or obscure the rhenium signal, and I think it has to do with floodplain and proglacial lake processes. And you can kind of imagine that for folks like me who also study the geologic record, our next steps will be to integrate things offshore from coastal cores or lakes that allow us to get at some of these fluxes through time and pair them to our studies of the modern watershed. So related to that, we're developing these data sets, as I've been talking about today, for a series of catchments in Utah, sort of Utah-Idaho region. This is Bear Lake, Salt Lake City's down here, and the Great Salt Lake. And we have a bunch of tributaries where we've been measuring uranium and uranium isotopes. And we're soon going to measure lithium isotopes on a bunch of these waters that are shown here. And then we've also measured the rhenium concentrations. And it does seem that the sites where you've recently deglaciated since the LGM and you have a bunch of Paleozoic sediments have higher rhenium concentrations in and around the lake itself, for example. So with that, I'd like to thank you all for your attention, and especially thank my former postdoc Evan and Sebastian Munoz, and then all of the collaborators that are listed here, and my funding from DOE and NSF that has funded the work that you saw today. So thank you.
Great. We have time for a couple questions.
Thanks, Dan. That was very interesting. I guess one interesting challenge in studying the role of glaciers is most of the samples we can collect reflect deglaciation. So I'm curious whether you think if we're in a time in the past where glaciers are actually growing, is there any pyrite oxidation, organic carbon oxidation occurring, and how can we sort of account for that when we extrapolate to the past?
Yeah, so that's what we've tried to do a little bit in that modeling of the ice sheets, but I totally agree with you. I think that in the past, when the glaciers would have been advancing, you would have primarily then been in the silicate weathering zone. And then during periods of ice loss, you perhaps move yourself into the source zone, and then you come back as you fully deglaciate. And so I haven't seen anyone do an interesting hydrologic budget and maybe a reactive transport model that allows us to interrogate that and then integrate that over, say, a glacial interglacial cycle for individual catchments. But I think that would be a really cool, fun modeling project to do. And it would almost certainly depend on the when the ice grows, how much it then is accessing, new fresh bedrock that has all that pyrite in it. So it's going to be catchment specific when you try to do that sort of modeling.
Thanks.
So, yeah, thanks for your talk, Dan. So in these glacial environments, they're also pretty productive. They bury a lot of organic carbon, right? There's humpback whales, I'm sure you saw
Yeah.
swimming around. And so I'm wondering if there's a role connected to the pyrite oxidation with the iron and the iron released and the productivity, in the Gulf of Alaska itself that could offset any of this.
Yeah, I have not thought about that, but that's an interesting point. So you take all that iron, you assume some stoichiometry between the excess iron and the additional productivity, and then calculate what that burial flux is relative to the sulfide oxidation flux. Yeah, I see where you're going with that. I suppose it's somewhat molar 1-to-1, like, because it's iron sulfate, like you can just kind of is very good, right? Yeah, that's a good point. I know, so Sarah Aarons at Scripps they did some work off the Gulf of Alaska thinking about the iron stuff, and I know at one point they were going to try to trace it to the rivers and the dust fluxes from this region, and I haven't seen any of that published work except the one paper looking at depth profiles of the iron isotopes, but I think that would be a really fruitful direction. Because, right, ultimately what we want to know is, for a given surface area of the land, what is the sink or source to the atmosphere, right? And so we need to account for those additional things that happen once the ions have left our catchment, right? Yeah.
We have a question, maybe comment over here.
Sorry.
know.
Thanks, Ian. I think you guys were saying different things though. As long as you move out of like the exact fjords, you move into iron limited pyrite formation, and the time scale for that is actually relatively rapid.
It's relatively fast, and so that iron is going to be sucked up and no longer be useful to the primary productivity.
And if the best looks that are probably the best looks that are probably in the kind of the area around Svalbard. Whereas if you're in the immediate very high accumulation rate, you have sulfide limited pyrite formation. But as long as you move out in most of those areas, you're in the more standard kind of coastal regime still, where you have biogeochemically reactive iron limited pyrite formation.
Right.
And the time scales for that will actually be relatively rapid, or it'll be on kind of the kind of diffusional.
So you really wouldn't have to. It really depends on the circulation then of the.
No, it just depends
water.
on the bounce. So in any of the fjords, the
Yep.
sediment accumulation rates are going to be high enough that you're going to be but that's totally what you're saying, Pete, from that. But what I was saying is actually a lot of the sediment, the majority of the sediment doesn't necessarily stay confined in the fjord. And if it moves out into it, the reactive iron that was created from the sulfide oxidation is going to then be removed and in effect be limiting sulfide oxidation, which will be limiting acidity production that will then re-equilibrate with bicarbonate and pore waters and re-equilibrate with the atmosphere. That actually wasn't my question. Sorry, that was an elaborate.
Okay,
comment.
but I guess just in response, like, that's super important, right? Because we're making this assumption that if you're in the source zone, that like the way that this triangle is assumed or comes up with from the stoichiometry is based on the residence times in the ocean. But if things are being impacted right at the coast, then like where things plot in this is then irrelevant whether it's a source or a sink. Right?
Yeah, I think that that would be a relatively easy one to try to quantify as well.
Right.
You could do it. You could do it either if you have a sense of how sediment mass accumulation will vary along these systems. You could do it with just simple diagenetic model.
Yeah, cool. So take some core, like a transective course out from one of the deltas or something like that.
That seems hard.
Well, you want to constrain
but you could
your model.
not opposed to making measurements per se, but I think without that. Do we have time for a quick question as well? So the quick question I had, sorry for that very long comment.
No problem.
Was when we were looking at lithium isotope and a lot of that, it seems like a lot of the lithium isotope values are going to be controlled by actually just equilibration with the exchangeable fraction, and that'll vary seasonally based on especially in areas that you have pronounced wet-dry cycles
Yeah.
and variations of your groundwater table.
Mhm.
How much, when you're looking at kind of arrays of lithium isotope results, do you think that we actually have a representative look of seasonal means, whereas especially when you think of it from outside of US and Europe, most of
Yeah, I
the-
don't think we do. I don't think we have the sort of high, I mean, I guess there's a couple data sets from China, right, that are pretty high resolution in terms of like several years of C delta Q relationships, but I don't think we have a good handle on that. And I think we're basically relying on the rivers to be big enough to integrate those signals, which relies on the transit times, sort of working out. And I totally agree with you. We've just made some measurements, not from Utah, but from Colorado, on a series of groundwater wells around a river that is relatively constant in its delta 7 lithium value. And we see values from 6 per mil up to 25 per mil in delta 7 lithium in the groundwater wells within that catchment. And it must have to do with essentially what you're talking about, seasonal changes and clay formation and other processes.
I would say it's maybe just exchange rather than clay formation, but
Okay, and then what about dissolution of the bedrock as well? Like seasonal dissolution?
well, I think yeah, it'd be interesting. I'd love to chat about. We're seeing kind of on weekly timescales swings of like 30 per mil in
Oh, wow.
groundwater wells. So that can't be related to clay formation. That has to be exchange reaction.
Yeah, I would agree with that. Okay, cool.
Okay, now we are out of time.
All right. Thank you. Sorry, you didn't get to ask your question. I know. I can see you.